For the last 3 years, the undisputed playbook in artificial intelligence has been simple. If you want to compete at the frontier, you pay what the industry calls the Nvidia tax. You buy tens of thousands of Hopper or Blackwell GPUs, you deal with whatever lead times you're handed, and you build your entire business model around standard merchant silicon. Every major tech giant eventually gets tired of that dependency. Google built the TPU, Amazon built Trainium and Inferentia, Meta built the MTIA. And now, OpenAI has officially entered the silicon arena. OpenAI just published the first measured benchmark results for Jalapeño, their first custom in-house processor. Developed in partnership with Broadcom, OpenAI already has physical silicon running tests in their lab, and according to their initial data, it's beating Nvidia's flagship Blackwell systems in power efficiency and latency on real-world open-source frontier models. Naturally, the internet did what it always does. Half of tech Twitter is declaring Nvidia dead, and the other half is calling it pure PR smoke and mirrors. Today, we're going to skip the knee-jerk reactions and do a proper engineering breakdown. We'll look at what Jalapeño actually is, how OpenAI designed it in just 9 months, what the raw benchmark numbers tell us, where the caveats are, and why this chip represents a massive shift in how AI companies will survive the economics of the inference era. Let's get into it. To understand why OpenAI built this chip, you have to understand a fundamental dividing line in machine learning, the difference between training and inference. Training is about raw, brute force mathematical compute. You feed trillions of tokens through a massive neural net to adjust weights. It takes months, eats millions of kilowatt hours, and demands maximum floating point operations. Inference, on the other hand, is what happens when you hit enter on ChatGPT. The model is already trained. Now, it has to generate tokens one by one in real time. And inference is an entirely different beast. It is brutally memory bandwidth bound. Every time an LLM produces a single token, it has to stream hundreds of billions of model parameters and context tokens through memory. General purpose GPUs like Nvidia's H100 or B200 are absolute marvels of engineering, but because they are designed to be great at everything, training, inference, scientific simulation, graphics, they inherently carry architectural overhead. If your only operational objective is serving conversational tokens as cheaply, quickly, and reliably as possible, much of that extra silicon real estate goes underutilized. This is precisely why OpenAI created Jalapeño. Led by their hardware division, OpenAI designed this processor as an application-specific integrated circuit, or ASIC, engineered exclusively for large language model inference. To build it, OpenAI partnered with Broadcom for the physical silicon implementation and networking silicon, with Celestica handling board and rack level systems integration. And here's where the hardware design gets fascinating. They integrated next-generation HBM4 memory, pushing memory bandwidth to an estimated 15.4 terabytes per second. That allows the chip to stream model weights into the compute logic significantly faster than current generation HBM3E hardware. They also capped the rated thermal design power at 700 watts, with actual measured sustained workloads sitting around 550 watts. Contrast that with modern AI data center accelerators pushing 1,000 to 1,200 watts per package. What's wild is the development speed. OpenAI claims the project moved from initial architecture to physical tapeout in just 9 months. According to the team, earlier generations of their own models helped design the chip and bring it up in the lab, while their newest models are now the ones accelerating how it gets optimized and programmed. That second part running on codecs, once the physical silicon already existed. AI literally helped design the physical chip meant to run AI. Let's talk about the data. When a company tests its own hardware, healthy skepticism is mandatory. But OpenAI didn't just test their own closed models behind closed doors. They ran Jalapeño through InferenceX, a public benchmarking standard built by semiconductor analysis firm SemiAnalysis. They tested Jalapeño across 3 large publicly available architectures: GPTOS 120B, which is OpenAI's open weights model, DeepSeek R1 670B, the popular open mixture of experts reasoning model, and Kimi K2.5, a massive third-party 1 trillion parameter mixture of experts model with only about 32 billion parameters active per token. Across all 3 models, OpenAI compared Jalapeño against the leading commercial inference benchmark results, specifically Nvidia's Blackwell GB200 and GB300 systems. When you look at the actual numbers, a few big things stand out. First, energy efficiency. Jalapeño delivered 1.5x to 1.9x more AI work per watt at peak throughput. On Kimi K2.5, the largest model tested, it hit approximately 1.5x higher throughput per kilowatt. And at a time when AI data centers are maxing out local power grids, performance per megawatt is the single metric that defines your bottom line. Second, latency. The chip delivered 1.7x to 3.6x lower end-to-end latency. For interactive workloads, meaning scenarios where an agent is thinking or a user is waiting on a live stream of text, it showed between 2.1x and 4.1x higher performance. Third, extreme single-stream speed. According to SemiAnalysis, during low concurrency testing with DeepSeek R1, Jalapeño achieved over 700 tokens per second per user. To put that number in perspective, the average human reads at roughly 3 to 4 words per second. You do not need 700 tokens per second simply to read an essay. Where that speed becomes transformative is in chain-of-thought reasoning and autonomous agentic workflows. When an AI model, like GPT 5.6 or Fable thinks, it generates hundreds or thousands of hidden reasoning tokens before outputting its final response. If your chip runs at 30 tokens per second, a 2,000 token internal monologue takes over a minute. At 500 to 700 tokens per second, that entire chain of thought happens in 2 to 4 seconds. For complex autonomous agents that call tools, inspect code, and iterate in a loop, low latency per token is the difference between a tool feeling like a sluggish batch script or feeling like a fluid instant collaborator. At this point, you might be wondering, how does a first-generation ASIC from a software lab beat Nvidia's premier hardware on these specific metrics? Did OpenAI suddenly discover some magic silicon physics that Nvidia didn't know about? Not at all. The secret isn't magic physics, it's specialization and co-design. Nvidia has to build hardware for everyone. A single Blackwell GPU needs to satisfy an enterprise training a weather forecasting model, a biomedical lab running molecular dynamics, a cloud provider renting raw VMs, and an AI startup serving a chatbot. That requires general-purpose compute units, expansive matrix engines, backwards compatible instruction sets, and broad architectural compromises. OpenAI doesn't have to care about molecular dynamics or legacy rendering. They know the exact mathematical profile of modern transformer and mixture of experts inference. They know exactly how attention mechanisms access the key value cache. They know the exact memory movement patterns between SRAM and HBM. They know how speculative decoding algorithms pass draft tokens between smaller and larger networks. And they know the networking fabric requirements needed to link chips within a single rack without paying massive power penalties for off-node communication. Because OpenAI designs both the frontier models and the serving infrastructure, they can tune the silicon directly to the matrix sizes, quantization formats, and memory kernels their models actually execute. OpenAI has been calling this their full-stack strategy. When your software team, your model researcher, and your chip architects sit in the same building, every software improvement makes the hardware more efficient, and every hardware refinement lowers the cost of serving the next model. It creates a compounding feedback loop. Now, let's pump the brakes for a moment. If you watch tech media, it's easy to get swept up in the narrative that OpenAI just rendered the entire merchant semiconductor industry obsolete. That is simply not true. Let's lay out 4 critical caveats that you need to keep in mind. First, vendor benchmarks versus production reality. These numbers come from engineering samples and lab benchmarks. Running clean open source weights in a controlled lab environment is very different from managing multi-tenant production clusters serving hundreds of millions of daily active users with dynamic traffic spikes, hardware failures, and real-time load balancing. OpenAI itself noted they won't even begin initial internal deployment until late 2026, with volume scaling slated for 2027. Second, the target is moving. OpenAI benchmarked Jalapeño against Nvidia's Blackwell GB200 and GB300. But semiconductor timelines are relentless. By the time Jalapeño deploys at scale in late 2026 and 2027, Nvidia's next-generation platform, Vera Rubin, will already be shipping to Tier 1 cloud providers, complete with its own HBM4 implementation and Rubin generation networking. OpenAI beat the current benchmark, but Nvidia isn't standing still. Third, Jalapeño cannot train models. Let's make this crystal clear. Jalapeño is strictly an inference ASIC. OpenAI still relies, and will continue to rely, on tens of thousands of Nvidia GPUs and third-party clusters to train frontier models like GPT 5.7 and whatever comes after it. In fact, Richard Ho explicitly went out of his way to emphasize that Nvidia remains an essential partner. Fourth, the software and compiler moat. Nvidia's real moat was never just the silicon. It was CUDA, CDNN, TensorRT LLM, and 2 decades of developer tooling. Building custom silicon means maintaining custom compilers, runtime libraries, and low-level kernels. Every time researchers invent a radical new architectural primitive that doesn't look like a standard transformer, custom hardware teams have to scramble to optimize for it. So why does Jalapeño matter if OpenAI is still buying Nvidia GPUs and still in the early stages of rollout? Because this isn't just a hardware story, it's an economic leverage story. Over the next decade, training costs may grow linearly or logarithmically, but inference costs will grow exponentially. Every search query, every autonomous coding task, every automated customer interaction runs on inference. If OpenAI relies 100% on commercial merchant silicon, their gross margins are permanently capped by Nvidia's 70% plus profit margins. By building Jalapeño, OpenAI accomplishes three crucial strategic goals. First, they cut the cost per token. Lowering power consumption by 40% to 50% directly reduces data center electricity and cooling overhead. Second, they establish supplier leverage. When Sam Altman sits down with Nvidia, AMD, or Microsoft to negotiate hardware allocations, having a working, high-performance in-house alternative changes the entire dynamic of the conversation. And third, they protect themselves against supply constraints. If merchant GPU allocations get choked by global demand, OpenAI can manufacture its own chips via Broadcom and TSMC to keep its consumer products online. OpenAI has already confirmed that a second-generation chip is deep in development, and a third generation is already taking shape behind it. We are witnessing the end of the one-size-fits-all AI computing era. The frontier is no longer just about who can scrape together the biggest training cluster. It's about who can build the most efficient, vertically integrated factory to serve intelligence to the world. Jalapeño proves that OpenAI wants to own that factory from the model weights down to the physical silicon. I want to hear your thoughts on this. Do you think custom inference ASICs like Jalapeño will fundamentally erode Nvidia's dominance? Or will Nvidia's rapid cadence with Vera Rubin keep them permanently one step ahead? Drop your perspective in the comments below. If you enjoyed this breakdown, hit that like button, subscribe, and turn on notifications so you don't miss our next deep dive into the latest in AI. Thanks for watching, and I'll see you in the next one.